Hello and welcome. In this video, we're going to learn about the derivative, one of the most important concepts in all of calculus, and we're going to learn about how it ties to a tangent line. So our goal in this video, I can find the derivative using the limit definition. Let's go ahead and jump right in. So we've already talked about what a secant line is. A secant line is a line that connects 2 points on a curve, and we tied that to the idea of if I wanted to approximate a function, I could find the slope between those 2 points on the curve. And that was our difference quotient. So we talked about the first point being x f of x, the second point being x plus h f of x plus h, and we found that fancy slope, or the difference quotient, the slope between the 2 points. If we could take one of those points and move it closer and closer to the other point, so minimizing that h, making that h almost non-existent, then we could actually find the slope of the tangent line at that particular point, a line that is tangent to the function. Tangent meaning it only touches the function once. And how do we do that? Well, we use what we've been building in the last chapter. We use limits. So we're going to tie limits to the difference quotient to define something called the derivative. All right, so the derivative is the slope of the tangent line. And every time you hear the word derivative, I want you to think slope of the tangent line. That is something that I want to stick with you. Slope is something we're really comfortable with, something we learned about in algebra. And this idea is foundational in calculus. So how we're going to find the slope in this lesson is we're going to use two things that we already know, limits and the difference quotient. Because if we're looking at that curve and we're trying to minimize the distance between 2 points, we're trying to approach h as it gets closer and closer to 0. What you're going to notice when you do this is that you're going to have to use a lot of those strategies that we just learned in the limit chapter. So a couple quick notation things. The way the derivative might be written, it might look like this, which is read f prime of x. It might be written like this, which means dy dx is how you would say that. You might be looking at d dx of f of x, meaning the derivative with respect to x of f of x. Or you might see it written as y prime. And we're going to use all these different notations. But the most important thing in this lesson, the derivative, is the slope of the tangent line. And I'm going to go ahead and just make a couple notes on how to pronounce and say those little notation pieces that you should add to your notes as well. So go ahead and pause the video. Make sure you write down anything that you might need. Most important thing, the derivative is the slope of the tangent line. Later on in this chapter, we're going to learn some shortcuts for finding the derivative, but all of those shortcuts come from the idea of using the limit as h approaches 0 of the difference quotient, and that's called the limit definition of the derivative. So when we're finding the derivative this way, which I promise we won't always find it this way, but when we're doing that, the very first thing we're going to do is apply the difference quotient. Then we're going to simplify. When we evaluate the limit, we're going to have issues with our denominator being 0. So that's where we're going to need to factor or use conjugates or use special trig limits so that we can actually evaluate that limit. Once we simplify, we're going to actually take the limit as h approaches 0. So as soon as we can, we're going to plug in 0 for our h values and simplify to get our function. And we're going to write the final answer using appropriate derivative notation. So let's look at this example. Step 1, we're going to take the limit of the difference quotient. So go ahead and pause the video and just write that first step of the difference quotient with the limit as h approaches 0. So I'm going to start with f prime of x, because that's what I'm trying to find, the derivative, is equal to the limit as h approaches 0 of 3 times x plus h, right? Plug in x plus h minus 3 times x all over h. Now, right now, I can't use direct substitution because if I tried to plug 0 in, I'm going to get indeterminate form. So we need to use some of those strategies. So let's go ahead and simplify the numerator. If I distribute the 3, I'm going to get 3x plus 3h minus 3x over h. So these 3x's are going to add to be 0. This 3h over h is going to simplify, and I'm actually going to just write that one step, 3h over h. The h's are going to divide out, so what's left is 3. So the derivative as a function of f of x equals 3x, that derivative is 3, which actually that should make a lot of sense. What kind of function is this? This is a line. What's the slope of this line? The slope of this line is always 3. What you're going to see with more complicated functions is that the slope is still going to have x's in it sometimes, most of the time, and that's because the slope is different as we approach different parts of the curve. Think about a quadratic. Over here, the slope is negative. Down here, the slope is 0. Coming back up, the slope is positive. So if we have a function that tells us what the derivative is, we can use that to find slopes anywhere along the curve. So that's ultimately where we are going, using the limit definition of derivative to find the function that'll tell us the slope of our original curve at any point in time for any value of x. Let's look at some more examples. All right, so we're just going to work through a few more examples. What I want you to do is start by writing f prime of x equals, and then go ahead and write the limit as h approaches 0 of the difference quotient. If you think you can simplify this on your own, I encourage you to pause the video and work through it. Then unpause the video and see how you did. So here's that first step with the difference quotient. Now I need to expand and combine like terms. Here we have that. Now I can combine like terms, negative 4x squared and positive 4x squared. And notice that each of these terms has an h that I can divide out. So let's simplify that. So if I divide this by h, I have 8x. If I divide this by h, I have 4h, and I no longer have a fraction, which means I can use direct substitution. Notice we're plugging in h equals 0. That means x is going to stay x. If I plug in 0 for h, what's left? Well, 8x plus 4 times 0, or just 8x. So f prime of x is equal to 8x. What that means is, if I want to find the slope of the tangent line to this quadratic at x equals -1, I could plug that in. I'm going to get -8. At x equals 0, I could plug that in and get 0. At x equals 3, I could plug that in and get 36. I could plug that in and get 24. So this function allows me to find the slope anywhere along the curve of that quadratic. All right, let's look at another example. All right, I think you can handle doing this one on your own. So start with f prime of x equals the limit as h approaches 0 of the difference quotient. Simplify x plus h to the third power, and then see how far you can get. And then unpause the video and see how you did. All right, so here we have the difference quotient with the limit, and then I've expanded. Now I'm going to combine like terms and divide out the h that they're all going to have in common. And now I can use direct substitution to plug in h. When I plug in h is 0, both of these terms are going to become 0, so f prime of x is going to be the function 3x squared. Let's look at one more example like this. All right, this one's a little challenging because there's some fraction work, but go ahead and set it up and see how far you can get, and then unpause the video and see how you did. All right, here's the first step there. Now, in order for us to be able to do anything, we really just need to simplify the numerator. So we need a common denominator, and I'm going to take this h and I'm going to write this as 1 over h so that I don't have to look at a fraction in a fraction. Now, to get a common denominator, this fraction needs to be multiplied by x over x, and this fraction needs to be multiplied by x plus h over x plus h. And when I do that, my new common denominator is going to be x times x plus h, and my numerator is going to be x minus h. And now I can combine like terms, so I have x and negative x. So I'm going to just rewrite this. The limit as h approaches 0 of 1 over h times, all that's left in the numerator here is minus h, and in the denominator we have x times x plus h. Well, look, these h's can divide out, so now we're going to have the limit as h approaches 0 of -1 over x times x plus h, and we can use direct substitution now, because if I plug in 0 for h, I'm going to get 1 over x times x, or 1 over -1 over x squared. So that is our derivative. we're going to push this topic to one last example, and then we're going to wrap up this video. All right, on this last example, we're going to use the limit definition to find the slope, and then we're going to use that to write the equation of the tangent line that passes through this point. So go ahead and pause the video, do the difference quotient with x squared minus 3, and then unpause the video and finish the problem with me. All right, so pause the video to check over this. Hopefully you had time to do that. So the derivative as a function we have right here. We want to write the derivative, we want to find the slope when x equals 4. So if we plug in 4, f prime of 4 is 2 times 4, which is 8. So this is our slope, and this is our point. And now we can write the equation of a line. Y minus 13 is equal to 8 times x minus 4. And we'll build on this idea of writing equations of tangent lines more in future sections. Let's go ahead and wrap up this section. All right, in this video, we defined that the derivative is the slope of the tangent line, and we learned how to find the derivative as a function using the limit definition. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.